Cn. Then we have a prior on the CND, which is this power spectrum of the CND. In this case, I will mostly be focusing on the CND polarization, and so this is E field of polarization that we're talking about here. I'm assuming that B modes here are 0. That's a simple possible transformation. So of course, we introduce B modes as well, and then solve this problem with the B modes as well. And then finally, we have another prior, which is this gravitational lensing field, which we assume is Gaussian, and therefore it comes with another Gaussian prior. All right, so this is the full problem, and you try to solve this on a map. Typically, would be a map of millions of pixels. All right, and so this becomes this very high-dimensional sampling optimization problem, where the goal actually is to get this power spectrum. But this is a hierarchical problem in the sense that we have two levels of hierarchy. One is the map itself, and the other one is the power spectrum of those maps. Okay, and so here are basically descriptions of what these different things are. But again, this is like these are two priors, and we're trying to sample both the parameters of the priors and the parameters of the fields themselves. And there are two fields here. One is the lensing field, and the other one is the CND field. Right, so it's a hard problem to solve. One method that we have developed over the years is this Muse marginal bias score expansion. I won't go into details. It first finds the maximum obscurity solution, but that's not all. You also need to run a bunch of simulations then to properly to obtain a proper solution for the power spectrum of, let's say, the E field and of the phi field. Okay, I won't go into details, but basically it's an approximation that turns out to be quite accurate. In this paper, what we have shown is that if you do this and you go to data such as South telescope, the 3G data, then, for example, if you just look at the amplitude of the lensing power spectrum, you find that this method reduces the errors by about a factor of 2.5 compared to the standard method. The standard method is called optimal quadratic distribution. Okay, so there's a lot of information to be gained by doing field level inference on the CND. That's the bottom line here. And indeed, this is what has been done by SPT collaboration. They have reconstructed both the lensing map. Here is shown in terms of kappa, so the Laplacian of the potential. And here is their unlensed E field. And here are the corresponding power spectra that can be compared to the other experiments. For example, ACT is here, but you see basically how SPT has recovered, because I'm showing here the true unlensed CNV. Lensing, what does, it smears out these acoustic peaks. But here we have recovered them back, and so in this particular work, they managed to recover 11 peaks. In contrast to what others are doing, such as ACT, where they're not doing this technique, and therefore basically okay, so that's one application of this method, and as a consequence, SPT extracts this information, lensing information, to very high accuracy, and it is very competitive with Planck and with ACT, even though it observes a much smaller area. I'll get back to these lensing constraints in a few slides. Okay, now this was done with this approximation called Muse. What we have been recently doing is we asked the question, well, can we do this with Monte Carlo Markov chain sampling, because that's a standard way to do this. However, there's a problem when you try to sample these very high dimensions. The problem, for example, can be seen in one of the very recent papers where they were trying to sample in 500,000 dimensions. They were trying to solve a similar problem, not exactly the same one. And basically, here are the sample numbers, and you can see how strongly correlated these samples are. Basically, this is omega matter, for example. You see omega matter changes. Over 10,000 samples doesn't change, but when I say 10,000 samples, these are samples from Monte Carlo. Each sample actually requires 30 calls. So we're talking about correlation length of order 1 million in order to get one independent sample. Okay, and now if each sample is a full forward model call, And if that full form model is very expensive, this becomes prohibitively expensive. All right, so that basically this problem took us then on a long but very fruitful path to ask the question: can we reduce basically the number of samples to get an independent sample? All right, can we reduce this correlation and in these very high dimensional problems? Okay. So, as I said, we have this took us on a very fruitful path. The first paper in this topic was by my student Jakob Brovnik, and we proposed this microcanonical Hamiltonian Monte Carlo. Let me just give you a quick idea of what this is about. First of all, Hamiltonian Monte Carlo, what it does is it enhances basically the system. Suppose you have a target from which you want to sample. What Hamiltonian Monte Carlo does, it creates a dynamical system, it adds momentum to this, and it treats this as a dynamical system. And then you follow basically these trajectories of a constant Hamiltonian for a while, and then you resample the momentum. Okay, and you keep doing this. And this would be the samples in the phase space. This is the position, this is the momentum. And when you project this down, you marginalize over the momentum, you get the target distribution. Okay, that's the basic idea of Hamiltonian Monte Carlo. We call this canonical method because the probability is proportional to e to the minus h. So we think of this as a multiplier, where h is the Hamiltonian, and Hamiltonian is this quantity here. Momentum squared over 2 plus potential. Right, so what we asked was the following question: can we do the same thing with microcanonical distributions, where we are conserving energy? The answer to this question is yes, we can, but the Hamiltonian is very, very strange in some sense. The potential term is the same, but the kinetic term actually picks up this log. It's a log of momentum squared. So it's very unusual dynamics that actually, again, you can show that if you project this down the momentum, you get exactly the same expression. Okay, just to show you how strange the dynamic is, so let's see if I can actually. This was supposed to be a video. Anyway, it was supposed to show the different dynamics of the two systems, just for you to have a sense how these different dynamic systems evolve. Let's skip this. Let me just go straight to. Let me go straight to the results from this sampler. We have run experiments on a whole bunch of different experiments. These are very standard Bayesian hierarchical problems. We're comparing to the standard sampler in the field, which is called no-U-turn sampler. It's based on Hamiltonian Monte Carlo. And you can see basically these are the effective sample size. Basically, the higher the better, right? You can see basically we're always much higher than nuts. And in some cases, actually, we are a lot higher. And so there are a couple of very nice properties of this sampler. Now we do have an implementation in blackjacks or with wrappers for an umpire and so on. So if you want to play with it, you want to try it out. Okay. Higher dimensional applications. The higher dimensional we go, the better this sampler performs compared to the baseline. So here actually is number of gradient columns to low error. So here actually lower is better. This is a simple Gaussian target with some dimension number of around 100. Basically this sampler is actually independent of dimensionality. It's the same cost regardless of dimensionality, whereas all of the other samplers, such as Hamiltonian Monte Carlo, they scale, they get more expensive as you go to higher dimensions. Okay, similar results are obtained. Now we have applied this to this CMB lensing problem that for which we used this muse before. And you can see basically this MC is actually quite comparable. Now here, higher is better. And you see basically MC is quite comparable to this muse technique, except that MC is exact, whereas muse is not, it's a approximation. And in all cases, these methods outperform Hamiltonian Monte Carlo by order of magnitude. So that's where we're heading next. Therefore, we'll probably replace the muse technique with this microcanonical Monte Carlo for these high-dimensional applications such as this. Okay, before I move on, I just want to tell you a few of the recent developments in this area. This area is all, it's a really different area from astronomy and cosmology, right? We publish in machine learning journals, but we have added a metropolis adjustment, which is not so important. We have developed some black box tuning. But the one that I'm actually particularly excited is we have developed an ensemble version where we run like hundreds of thousands of chains on a GPU. Alright, so we run them in parallel, and in terms of wall clock time, we obtain huge improvements compared to sequential methods, but also compared to the existing ensemble methods, which actually don't have here. But I mean, just to give an idea. Right, if you take a banana or I don't know, stochastic volatility, this would be our number, that's a wall clock time, this would be what sequential nuts would do. You can see basically often the differences are orders of magnitude faster wall clock times. So we're hoping that this method, this ensemble method will be particularly useful for people because as we all know, most of us are spending way too much time learning and waiting for the MCMC to emerge. Okay, we're also looking at various applications to molecular dynamics, condensed matter, lattice physicity, and so on. So those are also fields which require high precision sampling, so we'll benefit from this. All right, then we move on to the next part, which is variable utilizations with field level inference. This is actually what Adrian already covered, so I'll just quickly mention, I'll just go quickly through this. So basically, the current methods for variable utilizations are based on this standard reconstruction that has been discussed a lot. And we would like to go beyond that. And of course, what is exciting about this field is that DESI has found some anomalies which could be interpreted as the evidence for dynamical dark energy. And it's an extraordinary claim that requires extraordinary evidence. And the question is, how do we check that? And one way to check that is to try to improve and reduce the errors on the VAO using these field level inference methods. Right, so can we do better? And Adrian was already discussing this. These are slides from Adrian. Basically, there are two ways that we can do this. Either explicit inference, where we have a forward model and we try to infer the initial conditions using this hierarchical Bayesian approach, right, that we've already seen. Adrian's talk this. What do we need for this? We need a fast forward model. This will be, in this case, a full embodied simulation plus a galaxy model. And we need a fast sample. Okay, so in terms of differentiable n-body simulation, we have made a lot of progress over the years, which have now approaching a decade. We have fast PM, initially we have no PM, and now we have PMWT. These are all differentiable n-body codes, cheap n-body codes that are differentiable, and then we, first one was in C, this one was in TensorFlow, and now we have that. And then we have some galaxy formation model put on top of that. The amazing thing to me is that how fast these methods have become. We can run 100 million particles in a matter of seconds. So this forward model is really very fast. Okay. Now, we also need a fast sampler, and as I mentioned, we now have one. And this is actually work by this group, and I just want to shout out to this group because they have then shown that MCMC outperforms standard techniques like NUTS and HMC by order of magnitude or more. And this is basically number of relations for an effective sample. Think of this as, typically we will need about 100 effective samples. So that here you can see basically we need about 1,000 evaluations. So we're talking about 10 to the 5 evaluations, 100,000. And each evaluation is only a few seconds, as I mentioned. So this actually is feasible. Right? We can actually run 100,000 n-body simulations and reconstruct which conditions we experience. Alright, and this is shown on this plot where they show that they're reconstructing initial conditions and they're sampling. Alright, in our work we find similar evidence that LMC or MCHMC samples a lot better. You can see again similar plots to what I showed before. You see there's a very long correlation line for HMC. There's a lot more sampling, a lot more mixing in MCHMC. But we also have developed a different technique that Adrian already talked about, where we use implicit inference using convolutional neural networks to basically simply just reconstruct the initial conditions and then use pseudo likelihood using the power spectrum of those reconstruct initial conditions to develop basically a PAO on the spectrum. Right? And so we actually compare these two techniques. They are very comparable. And we're still actually exploring which one we should apply to real data. But what we have also observed is that in terms of figure we can get up to a factor of 2 improvements in terms of figure. So basically, we're talking about 30%. And we hope that this, 30% squared, it's almost 1.7. And that's basically the difference between 3-year data and 5-year data. So it's basically can lead to a huge change in terms of statistical power, and will enable us hopefully to test these methods, the results from this. All right. Now let me move on to the third part, which is gravitational lensing and single-use lensing. This is led mostly by B-Ray, but I also want to talk about some of the recent results. Led by another student, Jean-Louis, because I know that a lot of people here are in Hyper Spring Cam collaboration, and these are interesting results. Okay, so what's re-lensing? We have background galaxies, light propagates in the universe. As I said, it gets distorted by gravitational lensing effects. It gets observed, and so instead of having galaxies having serendipity, the distortion by lensing creates these shears basically the galaxies, and it creates the serendipicities that are forming. And so by measuring the correlations between these galaxies, we can reconstruct the maps of convergence, and we can of course measure the functions and so on. Okay, so let me introduce now basically the two main stage 4 collaborations that are already taking data. One is Hyper Spring Cam, which at the moment in their second release has given us about 400 square degrees of data to very, which is very deep. You get 18 galaxies per square minute. And then the other one is DESI, which is a spectroscopic survey and actually measures the galaxy redshifts very accurately. And there's some overlap between the two, which enables us to calibrate the photometric redshifts of Hyper Spring Cam. Okay, so let's see. So this is basically what HSC people have done. They have they've run the photometric redshifts predictions on the Hyper Spring Cam data, and they have divided them into 4 tomographic beams, as we call them, right? So the beams are from 1 to 2.6 and all the way to 1.2 to 1.5. All right, so they try to calibrate that using clustering technique, cross correlations between spectroscopic surveys and photometric surveys. Now, HSC actually didn't have such a surveys, but they have galaxy sample which has better photometric redshifts than the standard sample, and so that's what they did. But they ran out of the samples redshift. That's what the status was, and so they were missing a lot of data at higher redshifts, and for that reason, they decided to parameterize the redshifts observed with a shift, which essentially had no prior. And they just think in that shift together with cosmological parameters. The problem with this approach is that these shifts in the redshifts are almost completely degenerate with cosmological parameters, as I'll show in the slides. And so this really massively degraded the statistical power of HSC material analysis. Okay, so what we have done is we have done a similar technique, but we have taken DESI data. This is, in particular, this is DESI tier 2. And here I'm showing an example of cross-correlation between, let's say, spectroscopic beams in DESI, cross-correlating with one of the HSC beams. For example, here is beam from 0.2 to 0.6 and 0.6 to 0.9. You know, because this is a beam from 0.6 to 0.9, you know, it gives us almost no signal in the cross-correlation, which means that there probably are no galaxies in this beam at redshift 0.4 to 0.45. But on the other hand, this particular beam has a lot of signal in the cross-correlation here, which is not surprising because photometric redshifts say that it should be at redshift 0.45. And here we do this for several different spectroscopic beams. So this is basically the raw now data of this cross-correlation strengths as a function of redshift. We have done this actually for LRGs in DESI, for ELGs, and for quasars. So, and so here's what we find. These are our distributions compared to what photometric redshift technique has predicted. And you can see that, you know, in some cases there are shifts, right? In other words, photometric redshift prediction is not sufficiently accurate. For example, you can see here that our prediction is shifted towards the higher redshift. You see, the whole distribution is shifted towards higher redshift. Here on the beam 3, similar thing, but maybe a bit smaller. Beam 2 seems like photometers have done a good job, and on beam 1 actually is just the opposite, right? We see that our calibrations are shifting towards okay, here we're showing basically what these mean shifts are compared to the previous results. Again, you know, this is what I just said, right? That there are these shifts that on the means, and now we have very, very accurate priors on the mean redshift for these beams. In the process, we had to do a lot of corrections. For example, the first analysis actually didn't do any corrections at all. Here we applied the correction due to the redshift bias solution of the redshift sample, bias solution of the photometric sample. See, this one here actually, no bias solution. This one, the first one actually shifts the distribution quite a lot. This is called B1. Now this one actually is actually the easiest to do because we know exactly what the bias solution is. It's very easy to measure. The photometric one is actually harder to measure, but also it doesn't do much. And we can measure it using narrower bins. And then finally, we also apply the intrinsic line, magnification bias corrections. Again, it doesn't do much because these particular samples are not particularly strongly suffering from magnification bias. We use different scales from 4 to 3 megaparsecs, from 1 to 5 megaparsecs. You get very consistent results. In other words, we think that this is actually quite robust against negative bias. Okay, so the results are that here we are now comparing to the previous HSC analysis, which, as I said, because they put a very broad prior, the posteriors on these shifts in the photometric redshift calibration were very broad. Okay, our priors are very narrow compared to these posteriors that they have. All right, and so as a consequence, the other thing is worth noting is that there's a strong degeneracy between, let's see, cosmology, let's see, and we see the strong correlation, for example, between these shifts and the cosmology parameters, let's say it's the S8. Right? S8 is this particular combination of sigma 8 and omega matter that lens is particularly sensitive to. You can see basically there's a very strong degeneracy here, both of these being C3 and C4. And because of these very broad posteriors, this leads to a very broad distribution of S8 in the previous analysis. With the new prior, with the new photosync calibrations, this we put a very tight prior on these shifts, and as a result, we get much smaller error on S8. In fact, the error goes down by factor 1.8. But the other thing you'll notice, the value of S8 goes up. So here's a summary now, one of these awesome summaries of the current situation on S8. Here are the plan. Here's the summary of the CMB. This plan cross-act across SPT, and this this number comes down to 0.828 plus or minus 1%. This is the lensing constraint from CMB. These would be CMB lensing constraints, which include actually it should include. No, actually the other one. Sorry. This one is the lensing constraint. This one is the CMB. Right. This one is primary CMB. This one is the lensing, which combines SPT, ACT, and plan. And as I said, SPT, the measurement that I was talking about before, this one goes into this number. And all three of them are relevant here, plan, ACT, and SPT. Okay, so there's definitely no tension in S8 between CMB lensing and primary CMB. On the other hand, these would be the typical weak lensing measurements from before. This is the previous measurement from HSC. This is DS and so on. Now, the recent reanalysis of kids actually gives a number that is very consistent with CMB, and also very consistent when they combine kids and DS. So now this discrepancy between this and this, I still don't understand what's going on, but let's assume that this is what kids and DS give us. You see there are perfect consistency with Planck. And then finally, this work gives us these numbers, which are also very much consistent with Planck. So now when we combine everything, shear analysis give us this number here. You see how this is 1 part in 1,000 in agreement with Planck, right? I mean, it's a coincidence, but still. And then when we combine this number with this number, we get this number. And now suddenly we get a number which is also less than 1%. So we have a high precision cosmology in the weak lensing, but we also have a nearly perfect agreement with Planck primary telescopes. Okay, so at least on S8, it seems like from the weak lensing side there is no All right, let me move on and ask the question, can we do better using field level inference? And the answer is yes, we can. And how can we do this better? Well, as I discussed, we have several approaches. Explicit inference. I've already shown you this very high correlation number from that Uros Seljak paper. That one actually was using forward model, which is three-dimensional, but using lensing data, which is two-dimensional. So basically, there's a mismatch here between the lensing data, which is two-dimensional, but the forward models are all three-dimensional, right? Anybody's mentioning 3 dimensions. So it becomes really, really difficult. This is what we call high condition number problem, right? Because you have no resolution of the modes in the radial direction, and then there is only transfer modes, and this is very, very difficult to sample. So some people are still trying to do this, but I am actually very skeptical that this explicit inference will work on this. So instead, we decided to pursue implicit inference. And again, as I mentioned, right, there's 2 ways to do this. One is to do the posterior. We call this discriminative training because it's training on the labeled data. And then the other one is generative, where we learn the likelihood. It's conditional on the parameters, right? But this is more generative and basically less label-y because you need to learn the probability of the data first, and then you can have conditional inference on the parameters. Okay, this particular object is very, very high dimensional. Data are very high dimensional. And so the question is, how can one do this? Well, let me introduce normalizing flows as one of the possible techniques to do this. Normalizing flows are mappings from some very simple distribution, like a Gaussian, to some very complicated distribution. At each step of this mapping, you do some very simple transformation. Why simple? Well, because we have to be able to go in both directions, so we have to be able to invert this operation. And moreover, we have to be able to evaluate the density. To evaluate the density of the transformation, we need to evaluate this determinant of the Jacobian, right? So this f of f of z has to be very, very simple. Okay, so I'll show some examples of what we're doing with this for cosmology. Okay, but what can these normalizing flows do for cosmology or astronomy? Well, they can do all of the tasks that we're interested in. They can do sample generation, in other words, they can replace N-body solutions. They can do anomaly detection, in other words, they can find unknown unknowns, and, of course, most importantly, they can do inference. Okay, and so let me talk about one particular architecture we developed. It's called multi-state flow. But before I do that, let me just say a few words how we make the simulations. Right? Simulations have to be made. So we do ray tracing. We create, we run simulations. We run 3 different simulations at different resolutions. We combine them together. We create these maps. We do ray tracing so that we go beyond the border approximation. And so at the end of the day, we get maps that look like this. All these holes, this is actually a real, one of the HSC fields. All of these holes are basically stars that have to take them out. And so we do this now we typically generate tens of thousands of these organizations over over 100 different cosmologies. All right, so that's our training data. Then we need an architecture for the normalizing flows. We have developed this multi-state flow. The idea is that we take the high resolution two-dimensional image and we decompose it into low resolution and the differences. Okay, so one thing I should mention: normalizing flows are always they're not compressing any information. They're not losing any information. They have exactly the same dimensionality as the input data. And so here, right, we take this, in each 2 by 2 pixel, we average, and then we have 2 differences, right? So that's why we have exactly the same number of information here as here. But we can build now the dependencies of this one, for example, as the low resolution one plus the dependency of these 3 differences on the low resolution. So there's a conditional dependence here, and then we keep doing this. We resolve the low resolution one. We resolve it. We again decompose it into 4 maps and so on. Right? We keep going down in resolution. So that's basically an architecture which enables us then to build all the dependencies here and then we use various architectures to build those ones. Okay, so here is an example of using this method to generate a weak lensing map, a new realization of weak lensing map. So we start with a low resolution and then we upscale these three different maps to get this. We upscale again to get this. We upscale again to get this. This is the final map on a resolution which is roughly 100 minutes. And this will be the power spectrum we measure compared to the training data. Basically, we see the difference between the training data and our simulations, and also what the resolution function is essentially indistinguishable. So we think these are actually realistic simulations that can be then used for whatever one needs to use. However, as I said, that's not our main application. Our main application really is to do inference, for which we need to invert this likelihood using Bayes' theorem to get the posterior of the parameters given the data. But we can do this as a function of scale. We can do this on many different scales, and so we can compare the results on different scales. And that is actually one way to verify whether there's any problem with this equation. Okay, so here is an example of how we do this on 20 simulations. We do this on many simulations, and we compare the coverage, as we say, empirical coverage. In other words, because this is a likelihood method, it should give us it gives us a posterior. This posterior should reflect, in some sense, the errors. And the way to do this, you ask, well, how many of the simulations fall outside 95%, 90%, 85%, and so on. And you just go and count. That's what these plots are. And so, if the results are along the diagonal, then the errors are correct. If they are below the diagonal, the errors are overconfident, the method is overconfident, and if it's here, then it's conservative. Right? You see, basically, the goal is always to give correct errors, and that's what we actually do. Okay, so what about interpretability? These methods do give you some sense of interpretability. For example, say this is an input map, and you pass this to these generative models, and you get these posteriors, and let's say posterior says image should be equal to 6. Now you ask, okay, why isn't it plan value going to 8.6? Okay, you can go in reverse and you can actually you go reverse to these noise and go add this conditional value, and you get this map. And now you can take the difference between these two and ask where the information is coming from. And so not surprisingly, right, that all information is coming from these high density regions, right? Protoclusters, clusters, or maybe some broader regions like clusters. People that do cluster cosmology, of course, know that there's a lot of information in clusters, but really, you can't really pin it down to just clusters. It's really the cluster environment and things like that. That's where most of these differences between, let's say, high superconductors. Okay. Now, what is this method going to give us? I don't know the answer. We're still working on it. But in some of our preliminary analysis on the simulation still, with a whole bunch of marginalization parameters. For example, we do variable feedback parameters, we do intrinsic alignment parameters, and so on. We do obtain improvements on S8 and omega L, which can be quite dramatic. Okay, so maybe up to a factor of 2-ish. And so if that, we can achieve this, and again, this is on realistic simulations of hyperspheric camp. And if we can achieve this, then really this is going to be an impressive result that will further, make, for example, HC data even further in the leaders in terms of influencing information. Okay, so I've talked about this generative model, but let me just say a few words about this discriminative approach, where you go straight from the posterior. In fact, we had reclassing a certain challenge at Uros. Uros is the biggest conference in machine learning, and we just had it last weekend in San Diego. My former student, Peter Dye, was the lead of this challenge. And so what we did was we gave people these maps that I was just telling them about. Well, one of the maps, one of the largest fields in HSC. And we asked them, well, how well can you get the cosmology out of it, but also how well can you determine the uncertainty of the parameters. And I was impressed by the response. We got hundreds of entries, and we got some very impressive techniques that I for sure will study and see if there's anything I can learn, and there's anything we should adopt for our real data analysis. But basically, the idea was, very similar to what I said. We create these maps. We had noise. We had baryon effects. We had this redshift uncertainty, and then we passed all these maps to faults. We created about 50,000 maps, and we get we labeled data. We gave them, and so we asked them, okay, go ahead and tell them the numbers and tell us what the error is. So. So here's basically roughly what the consuming power came out to be from the best entries. This is the power spectrum I mentioned before. This is figurametric. Okay, this is error on inverse error on the S8 times the error on omega matter. Okay. So the power spectrum will get this scattering transform that has been allocated as being a much more powerful technique than power spectrum. Gives us maybe about a factor of 3 times more consuming power, but CNNs, typically solutions for all CNNs, give us another factor of 2-ish, right, to the point that our figurametric actually turns out to be 4 or 5 times bigger than the power spectrum. Now this one was done for very low noise. We assume here 30 galaxies per arc minute. HSC doesn't have 30, it has only 15. So we expect that the actual application for HSC, the improvement will be a bit less than this, but nevertheless, as I said, we can expect about up to a factor of 2 improvement on each parameter, which will be a factor of 4. Okay, so all right, this is a scoring metric that I will not go into it, but I'll just mention that we also have part 2, which we haven't done yet, but there will be alpha diffusion detection, and so if anybody's interested in these techniques, Okay, here are the winners on the generalization, which is when we generalize to the unseen cosmologies and unseen data. It turns out that the winner is this person. He's I don't even know what, a student, I think, out of India. He developed this CNN approach using dense net. He used various tricks ensembling, k-folding, and stuff like that, and obtained the best results. François Lanoux, who is probably the best known machine learner in the field of cosmology, was tied for a second. François Lanoux and his team, I should say. There was also actually, I'm not showing here, there's also a CB agent led by Boris Boyer that actually on the non-generalized data came out first, but didn't generalize very well, so that's why it actually dropped out of this data. But it's an interesting development that agents actually are also being quite competitive in terms of these approaches. All right, so at the end of my talk, I just want to summarize basically. At present, lambda CDM standard model is holding up quite well, I think. As tension is disappearing. We'll have to see what's up with those DESI dynamic about energy results. But there's also a lot of opportunities where field level inference can actually significantly improve the results. And as always, any significant improvement has the potential for a major discovery. Maybe discover something, maybe not, maybe we'll be lucky, right? And I would say certainly that testing this DESI result is probably the first place to see if we can get lucky and find some major discovery. Maybe in terms of confirming what the things are, or maybe something else. I do believe the field level inference is finally ripe for application for real data. It's been a long time coming, I would say. We have been making these claims about machine learning, taking over cosmology, and it hasn't really happened yet, right? But I do feel that we are now at the verge of actually achieving significant improvements over the standard power based inference. And finally, I'll just mention that this journey to do the field level inference has actually taken us to find applications, to develop techniques and find applications which are quite far out of cosmology. As I mentioned, this MCMC is a method that has now been applying to Bayesian statistics, lattice QCD statistics, and so on. So it's really, I think, rewarding to see this. People outside our field are applying this technique now, and in some cases, okay, with that, I'll stop here. Thank you.
Thank you very much. Time for questions.
Thank you, so impressive. I have a question about the simulations. You showed the plot where you compare the CLs from your simulations.
CLs?
Or the power spectra or something.
Which one, sorry?
I think for the simulations for the HSC inference, I believe.
Oh, HSC. Oh, CLs?
Because there was a small plot in the center. Yeah, that one.
Wait.
On the two slides forward, I think.
Oh, forward.
Yeah, here.
Oh, this. Okay, sorry.
So could you comment on this? How did you get that?
Well, this is basically the idea here is that normality flows can be a generative model. In other words, you train this on 50,000 simulations, and now you can create new organizations of simulations that, at least at the level of statistics we have looked at, they look indistinguishable from the simulations that are going into the training data. In other words. And so you can think of this as now as a simulator, as a fast simulator, because this is extremely fast now, right? Once you've trained this normality flow, generating new maps like this with different seeds, different random numbers, is extremely fast, right?
I see. So this is the comparison of your machine learning or your flows with respect to the simulator.
Yeah.
Right? So are you concerned that maybe because this is something like fast based simulator, that you can have some kind of bias with not recovering these small scales?
So we use three simulation boxes. The first one, the lowest one, is Gadget, right? Which actually, for the reasons you just said, right? Because FastPM doesn't have enough resolution of lower versions, and then we use. Okay, the next one is I think FastPM at maybe 300 megaparsec, and the next one is maybe FastPM 1,000 parsecs or something like that. Right? So as you go to more distant, to larger distance, a given angle converts to larger physical scale, and so you don't need as much resolution.
You use a fast simulator to initialize gadget on the overhead chip or something like that?
Sorry, so
You use the high fidelity sim, the gadget is initialized at the overhead chip from the fast simulation, so it's independent runs.
No, it's an independent run.
This normalizing flow is certainly very interesting, but one aspect which you mentioned is about looking for the anomalies, right? So many simulations that you use based on, let's say, conventional cosmology and can make tighter constraints on the parameter, that is fine. But if the background cosmology is not what you are making your simulation based on, can this anomaly detection be used to say that something is different than what we are simulating based on?
Yeah, it's an interesting question. I skipped the slide on anomaly detection, but I have one. The density of these anomalies and flows, you see, because we're doing this density of a field, we call this density of data, right? This number can be used as an anomaly detector. And in fact, interesting story is that when we applied our simulations to the HSC data, we found that the density was too low. Density of the data. That means that we were missing something in the simulation, right? And so we found an anomaly. Right? It was actually, we found an unknown. Then when we thought about what we missed, we realized that we did not put the clustering of the sources in there. And once we put the clustering of the sources in there, this anomaly went away. So these techniques can enable you to find unknown unknowns. I'm not saying this density is the best method out there. In fact, it's a very good challenge, which is why I'm part 2 of the challenge. I'm actually very much looking forward to that to see what people will come up with in terms of unknown detections.
Ali?
Just a short question. So this is very highly related to diffusion models, the normalizing flows. What is their advantage? They're much faster than the fusion?
Diffusion models are very expensive to train because they're continuous, and their density estimation is not necessarily very good. So diffusion models are very good for this other task, right? Diffusion models are very good for this, for generating new data, right? Yeah. But in terms of for the inference, I don't think they have been tested very well, and when they have been tested, I don't think they have shown very good performance.
Okay.
Any other questions? I had a question on the lensing field level influence, where, for instance, like the SPT data, you said if you simultaneously actually try to reconstruct the unlensed field at the same time as you reconstruct the lensing potential. Do you understand it right that you are able to generate, is it a unique CMB realization that goes in, or is it a random walk because you simultaneously have to fit for the CMB unlensed map, whatever, a pre-lensed map, but the lensing field? Because I would have naively thought, well, you have one observable, you're trying to generate two fields out of one measurement.
Well, no, actually, you have two observables.
Evo.
Evo is also an observable.
You mean big zero.
Yeah, big zero. Yeah. So actually, you have E and B observable. So you have two fields that you're covering two other fields. Unless
so you get a unique. This unless is meant to be a unique.
Okay, let me phrase it like this. In the absence of noise, the solution is unique. In fact, back in 2003, in the papers I wrote with Trisky we have shown that as the noise goes down, this limits on B and all that go down, which is a statement you can de-lens perfectly, and the statement is in the solve this problem precisely because the count is equal number of equations as the number of parameters.
Okay, in that case, thanks so much again for a wonderful closure.